Okay, we'll go ahead and get started, everyone. So if you haven't got anything to eat, got plenty of food back there. So thank everyone for coming out today. I want to do just a little overview, a few slides before we get started and introduce our speaker. First off, we always like to thank our sponsors. So here's a list of all of the sponsors for the ISA New Orleans section. Anybody's interested in being a sponsor, it's $150 a year. And you can go to our website and sign up, and we'll get your logo and write up on your company there. And it definitely helps us put on these programs, helps us keep the meals free for those that are members, and low cost for those that are not members. So we appreciate all of our sponsors. Last month we did our symposium and expo. So we had last month we had the District Leadership Conference was here in New Orleans. We hosted, so the New Orleans chapter hosted the District Leadership Conference, which was all the sections in Texas and Louisiana getting together, the leadership from those. We had that at the Hilton Garden Inn, and because we had the Hilton Garden Inn booked for that meeting, we decided to hold a tabletop and expo. So we had Art Zadaran, who's here, did a session for us for those who are looking to get their ethics credit. Did a very wonderful session on things that he's seen in the forensic profession. And Paul Gruen came in. Paul is the ISA president for international president. He's based out of Houston. He came in as a safety expert and did a great safety topic, talked about Texas City disaster and causes of that. And then we had a tabletop expo. As a result, we signed up some new sponsors for that. So we've increased our sponsors now. And so here are our new sponsors. And we'll thank them for joining the section as well and sponsoring us. Next month, we're going to be in Delgado at the Fab Lab. So Wayne Welk, our webmaster, is one of the instructors at Delgado. And he got us hooked up with his neighbor down the hall at Delgado that runs the Fab Lab. So that's an area where, I don't know if you're familiar with it, but it's sponsored. Chevron put in a lot of money to build the lab. It's a lab design that was designed by MIT, and there's only a handful of these in the world, maybe 10, 12 of these labs in the world. But only one in Louisiana, and it's at Delgado. So it's laser printer, laser cutters, 3D printers, lathe machines. I mean, it's a lot of different design tools. So we're going to run down of that lab. And with that, I want to introduce our speaker. So Frank Ruiz has come in. Son Dean's in the back. The other Dean, we like to say, we go back and forth. So Frank, 54 years in the industry, 32 with Dow Chemical, and the last 22 as an industry consultant. Most of that with Parker, consulting on analyzer systems, pressure loop control systems. He holds several patents, and yeah, so it looks like we have a very good turnout today. So both here and online. How many do we have online today? Like another 3 or 4. Okay, and some more were signed up. So. So please give a warm welcome to Frank Ruiz.
I'm green. All right. All right. Thank you, Dean. Thank you, Dean. I also have another son who's visiting from Maryland. He drove down with me. I'm from Allen. I'm from Baton Rouge, well, right outside of Baton Rouge. That's where we live right now. So Dean invited me to speak today, and one of the things picked was analyzer sample handling system. I don't know You guys are heavy in the analyzers, but this is a solution to a problem primarily for the analyzer industry. So let's see. Introduction, we've already talked about introduction. I worked for Parker Hannifin. Prior to that was Veriflow Regulators, and prior to that was Dow Chemical, and prior to that was Destech coal gasification. So we got a lot of miles on this, so to speak. But Parker has gotten into the analyzer end of it pretty good. So I want to talk about the purpose of the system. What does it do? What problems does it solve? System overview, and then any kind of questions you might have. A purpose of this system is to collect the sample. All analyzers require a sample flow from the process line, transport it, analyze it, then you have to dispose of it. So this system handles that, manages that part of the process. It provides the analyzer with a very stable vent pressure. Okay, most of these analyzers, the measurement cell operates under atmospheric pressure, or whatever pressure it operates under, it has to be stable and it has to be constant. It could be an elevated pressure, or as long as it's constant. Most people used to use atmosphere because that's fairly constant and it's easier to use because it's always there. Then we have also environmental regulations now. The EPA guys come along and says you can't do that anymore. You have to collect these samples, control where they go, and dispose of them properly, typically a flare header, or back into the suction of a process, a compressor or something, or back into the process. So you have to get it, analyze it, and get rid of it. And you have to minimize any kind of contact with humans. You got some really bad stuff out there. I did this just as an exercise. Is what kind of flows are we talking about out of an analyzer? A typical analyzer is going to have 4 liters a minute flow. That includes the sample through the analyzer and what's called a fast loop sample. Okay, so 4 liters a minute is fairly common. So if you do that 4 times 1440 minutes per day, you're talking 2 million liters per day. 74,000 cubic feet a year. And if you use air as a density, as an example, 5,000 pounds of stuff per year. If you got 1,000 analyzers, that's 5 million pounds of stuff per year going somewheres. You say, well, who's got 1,000 analyzers? Well, a lot of people's got 1,000 analyzers. I worked at Dow, we had 1,200 analyzers. Exxon and Baton Rouge probably had over 1,000 analyzers. There's a lot of facilities with 1,000 analyzers, but you can figure out how many you want. 5 million pounds a year is certainly significant enough to manage it, collect it. So in the old days, you'd vent, your analyzer would be vented to atmosphere. So you take a sample out of the process line, you'd regulate the pressure down, control it through a rotometer needle valve into a continuous analyzer or GC, wherever you want to go, into this vent header. A vent header is a collection header that's usually in the analyzer shelter. And it collects all the effluents from the analyzers. Then it goes from there somewheres. Used to go to atmosphere. That means that the analyzer cell here is basically floating on atmospheric pressure, which is fairly constant and everybody's happy, except the EPA. So what you have started doing is putting in a back pressure regulator right here. So what happens is it comes through just like before, except instead of going back to the flare, they go through the vent header and the back pressure regulator. So the purpose of this guy is to back pressure the analyzer at a pressure above the fluctuation that you occur in the flare. So a flare header typically runs anywhere from a ½ pound to 1 or 2 pounds on a normal day. So if you set this thing at 3 pounds, that means that you're controlling and operating over here above the fluctuation on this flare. However, what happens when the flare shoots up? And it happens actually quite often. So this regulator, if it's set at 3 pounds and you have 5, 6, 10, 20 pounds over here, your flow stops. Your analyzer cannot flow from 3 pounds to 20 pounds. So you got to do something about it. This is fairly typical, and a lot of people live with this today. They just set a back pressure regulator right here. That also means that your analyzer is running at an elevated pressure, whether you want to or not. A lot of analyzers, you don't want to run them at elevated pressure. A lot of measurement cells can't handle 3 pounds or 10 pounds or whatever. So, but this is fairly common. And so what's the solution to this? Is put in a pressure system that collects what comes out of the header and pumps it to the flare at whatever pressure. So this guy right here, whatever this thing is maintaining a constant pressure in the vent while this is going all over the place. So it's totally isolating this pressure from that pressure. By the way, this system is an operating system, been out for 15 years, literally all over the world, and it's very successful. It works great. And the way it works, it's very simple. Usually simple works better. This pipe could be your vent header that you're trying to control. All right. So you put a regulator on one end, it controls the pressure in this pipe, and you take the flow out over here. So as you take flow out, the regulator makes it up, and you maintain a constant pressure in the header, and everybody's happy. So if you start contributing flows into the header, and you're still taking out 20 liters a minute, now you're putting in 8 over here, and you're taking out 20, this guy only has to put in 12. But again, it's maintaining a constant pressure by controlling the balance. If you keep adding flows to it, you got 8, 6, 14 going in here. These could be coming from analyzers, and you're taking out 20. So this guy over here drops down to 6. So the key to this thing to maintain a constant pressure in this header is absolutely important, is that you have to take out more than you're putting in. So this guy can always stay flowing, controlling the pressure. And it works quite well. So what happens if this pressure over here exceeds the vent header pressure? Well, you have to have a pump. So some of these back pressures, planner comes and say, well, man, we get the 35-pound back pressure sometimes. What are you gonna do about that? Put a pump on it. So the bottom line is, if you can pump it, this thing will work. The thing is, you got to pump it, and you got to find a pump that will pump into whatever back pressures you're exposed to. So a typical system uses a solid state pump, eductor. I call it eductor, aspirator, or whatever you want to call it. Take a motive force gas, discharge it through this tail section, and you produce a suction here. And they're very, no moving parts. These things will sit out there for years and years and years, and no moving parts, as opposed to a mechanical pump. So this guy is sucking on this needle valve right here. So that says you can operate this vent header at atmospheric pressure, literally at zero gauge pressure, which is your analyzers typically operate anyhow. So if this is running at 0 and it's sucking on it right here, this is typically run at -6 inches of mercury. So that's about a 3-pound drop that you have across this needle valve right here. That's your flow control. So you're controlling the suction pressure here on this eductor, and you're controlling the flow through this needle valve by controlling the differential across the needle valve. So you got 0 here, -3 here, so you got 3 pounds of differential to adjust your flow. So you got a good flow control system there. So the problem here is this eductor. In order for an eductor to work against a back pressure, they don't like back pressures. So you have to put a lot of motive force gas into them. So it takes a big eductor to work against 20 pounds of back pressure and still flow 20 liters a minute through this side of it. So what we incorporated is a economizer circuit, if you will. It's right here. So what this guy does, it looks at the vacuum that this eductor is pulling, and it throttles this pneumatic booster relay, multiplying booster relay, essentially. So if this vacuum starts to diminish, in other words, get more positive, we lose in vacuum because the back pressure is increasing, because the flare pressure is going up. You start losing vacuum, or try to start losing vacuum. This guy right here is looking at this vacuum, say, whoop, we got to boost this up a little bit, drive this guy a little harder. And that's what it does. The pressure typically from this motive force gas pressure could change from, I have a chart later, but it's anywhere from 15 pounds to 100 pounds, depending on how much back pressure the flare is producing over here. So it saves a lot on the gas. All right, that guy right there, you've probably seen before. If you walk outside your house and look at your gas meter, you'll see one of these things. This is a very sensitive pressure regulator. And it's a very reliable regulator. So why are you using this thing? Because it's so damn sensitive. This thing can control within 1/10 of an inch of water, and which is way beyond what you need for a typical analyzer system. Also, you can get by with a carbon steel body. So yeah, but I got all kind of bad stuff in my header. How are you going to get by with a carbon steel body? Well, the stuff in your header doesn't pass through this regulator. The only thing goes through here is the nitrogen making up the header. So it doesn't see any corrosives or things like it, as opposed to if you was to put something like that on your vent header, like a back pressure regulator, everything in the header would have to pass through the back pressure regulator. So you'd have to have some exotic metallurgy to handle those kind of applications. Where this guy, you can use literally carbon steel. So to test the how well a regulator controls, and a regulator is a proportional only controller, a very crude proportional only controller, which says that if you change the flow through it, you're going to get a different pressure. It's just got to do that. So that's the only way to work. So to test that regulator, you go from 0 to 18 liters a minute, which is the maximum variation you're going to occur on that regulator. And actually, typically it stays like, right in the middle of that curve right there. So you're not going to be with it very much. But the worst case is 0.3 inches of water. So we control the atmospheric pressure, and this thing's holding it within, it's literally holds it within a 0.1 inch. But the only way to test it is to get your YouTube water manometer and look at the meniscus in there, and it just doesn't hardly move. It's just so sensitive. So, all right. That regulator is right there. So this guy sits on the header. So what it's doing, it's controlling the pressure right here on that header. It's not controlling it there, it's controlling it right there. So with that, the caution is you don't want small tubing for a header because you get pressure gradient, those kind of things. So you want to make sure that this is big and the flows are low, so you have pressure over here can be really close to the pressure that you're controlling. So if you provide this regulator with a source of supply pressure, it will pressure this header up as necessary to maintain that pressure balance. And while you're sucking it out over here with your reductor, and your analyzers are putting it in over here. So you might note that this regulator, when you order a regulator like that, have a range spring in it. 1 to 3 inches of water, 6 inches, whatever range you want. Just most people want to run their analyzers at 0 because that's a good place to run them. So what we do is we open this guy right here, take the range spring out. There's no range spring in it. So, well, it can't work without a range spring. Well, sure it can. What this regulator does, it's a differential device. It controls pressure versus a reference. So if the reference is atmosphere, it's going to control at atmosphere. The spring only adds bias. I want atmosphere plus 5 inches. Well, then you got to have a spring because you want the 5 inches. But if you don't put the spring in, you're going to stay at atmosphere. It's very sensitive. In fact, you can put it in one plane, you get one pressure, and if you rotate it, just the weight of the diaphragm, you might get a 1/4 inch of water difference. So, but whatever it is, it's very stable right there. It typically comes up around a 1/2 inch of water. Okay, so this is the pressure control part of it right here. This does all the pressure controlling. This is the pump. It doesn't look like a pump, but that's what it does. It sucks out of here and goes out to a flare or wherever you want to go. And a typical system looks like this. This nitrogen supply regulator maintains a pressure to this box for pneumatic. It's a pneumatic device, old school pneumatic device. And then right here is your vent header pressure gauge, eductor motive force pressure. So that guy changes with the back pressure from the flare. And then here's your vacuum. This will stay fairly constant. Doesn't have to be perfectly stable all the time, but that's your differential across this needle valve right here that controls the flow rate. So you got two flow pressure controls going on. You got a flow control and right with this needle valve differential, and you got the big regulator controlling the pressure in the header. So you got a very stable system. This is the system. Again, it takes about 100 pounds of supply gas. Typically, that's nitrogen. A lot of plants use natural gas. So natural gas will drive these eductors just like nitrogen will. What's inside the flow path inside here, you go through the rotometer, in the inductor and out. So this is your quote wetted path right here. So if you have some really corrosive devices, you only have to concern yourself with the eductor and the rotometer. This could be an armored rotometer or a glass rotometer. The eductor, this typically shows the section, the performance of an eductor. They got different size eductors. This is the biggest one, we call it A eductor. And why you have different size eductors is because you want to absolutely minimize your motive force gas usage. So you look at these charts and you say, well, I can get by with the smallest eductor based on what the maximum back pressure I expect to see. So if you got the worst case and you're going to go to 20 pounds of back pressure and 20 to 25 liters per minute of sample flow, then you need a bigger eductor. That's A ductor, and then they got what's called a B ductor, which means it's a little smaller, and then they got the C ductor. It's even the smallest. So if you're not going above, say, right pressure, 5, 8 pounds of back pressure, you can still get a lot of flow through that guy. And that eductor literally is the size of a 1/4-inch tubing T. It looks just like one. You can't really tell the difference between a 1/4-inch tubing T. That's how small that thing is. All right, this is a nitrogen usage on these 3 eductors, A, B, and C. Typically, your flare pressure is relatively low, and you're going to be kind of in this region right here. So you're not going to be using a lot of nitrogen. You can't run these off a bottle, but most plants have nitrogen service anyhow. So. This is EDR, we just call a natural gas. So the model before that uses nitrogen. So some of the relays in there breathe to atmosphere, so it might breathe a little nitrogen out. But if you're running it on natural gas, you probably don't want this thing breathing natural gas on it. So we have a model that doesn't breathe. It's a non-bleed type. That's what the NB is right there. So there's a lot of these guys in these plants, gas plants that use this version, and they use natural gas as a motive force gas. A pump, we've had these things will handle. Typically, a pump is I don't know if you're familiar with ADI. It's a little vibrating diaphragm pump. Is typically what's used on these things, and they'll handle 25, 30, 40 pounds of back pressure. We've had some of these systems go up to 80, 90 pounds of back pressure and 200 liters a minute. So once again, the limiting factor to this thing operating is this guy right here, the pump. You can pump it, it'll control the pressure. And so what about liquids? Can this thing handle liquid? Well, you don't want to get a solid flow of liquid in your system, just a gas system. So you need to handle it down on the headers over here. If you expect to have a lot of condensation going on in your header, liquids collecting, you probably need to slope this down to some sort of a liquid sump pump combination. And this pressure, you're basically controlling the head pressure on that trap. All right, this is some analyzers don't want atmospheric pressure, like TDLs, as an example. They want to operate on the negative pressures. Lower the pressure, the more sensitive they are typically. So you can operate this header as this particular one was like -7 pounds. So it's a hell of a vacuum on this thing, but the analyzer was floating on that header. And we use a different regulator here for negative pressures. But this over here works the same. It's just operating at a negative pressure. You can even get the ductors to go down to some pretty negative pressures, or you can put pumps on them. They also, let's say you have a system where you already have a scavenging system in your plant that runs on a negative pressure. Well, you got one that you just connect this to that. It's just looking for a lower pressure to go to, basically. If you got a lower pressure somewhere, it's fine. And this sort of adjusts the load through this system. This system can't change your plant system, so you kind of isolate it with this load valve, if you will. All right. That's a different regulator. These regulators, that first regulator I showed you was they have internal relief valves on them. And some plants said, I don't want any relief valve on my regulator. It's okay, no problem. You can get that regulator without a relief valve. And I said, well, I don't know if I want that regulator anyhow. Well, you can put this guy right here. This is a metal diaphragm regulator, standard analyzer, grade type regulator, and you can change the set point wherever you want it. Okay, this is another way to do it. This is different ways how you can hook these things up. For instance, this regulator, the big guy, has a dome vent on it. And you should never, ever connect that dome to a flare or someplace like that, because that's your reference pressure for your regulator. If you stick this thing, connect this to a collection system somewhere, that regulator is going to follow that collection system pressure. So you don't have anything stable anymore. So typically this is atmospheric pressure. So if you're concerned about the relief valve opening up in it, then you can vent this to a atmospheric header, which has a little loop or whatever, but you have to maintain it at a constant atmospheric pressure. And then the pump, you can have another regulator. So what you have here are dual headers. You got this header running at atmospheric pressure, and you have this header running wherever you want it, like for fast loops. Another thing about this header right here is pulsating flows. These regulators can only do so much controlling the pressure. And typically what's happening is that the regulator is only putting gas in the header. It can't take gas out of the header. So if you blast that header with a pulse of pressure somewhere, you have to wait for the normal flow to pull it back down to set point. Okay, so you don't want to pulse these guys, but you can pulse the hell out of this. So you can, a lot of like stream switching valves, you have a double block and bleed, and when they switch, you take the bleed or the pulse and you send it somewhere. Well, you can send it right here. It's not, you can pulse this guy, but you don't want to send it right there. So that you need to minimize the pulsing going on in the header. This is a this vent system with a standby pump. So typically a flare is not going to run 30 pounds of pressure. That's crazy. I mean, with Dow, we used to have these big flares, a 36-inch feed line to it. And when that thing was flaring wide open, the ground was shaking. You know, it was really bad. So how often does that happen? Every 2 years or something like that. So you don't want to have to run a pump, mechanical pump, for 2 years waiting for that situation to occur. So you can run this thing on a eductor, which you're normally going to run within the 20-pound range. And if it ever goes to the high pressure, you can put a switch on it, high pressure switch, turn on the pump, and it will discharge through these check valves. So this is it's called a sonic choke. Sonic choke is a device that will, it's basically a flow controller, if you will. It's a solid state flow restrictor. So once this thing is choked, you can't increase the flow. So you size this guy for the maximum flow that you want to take out of this header and just let her eat. Worked good. All right, this is this is basically the same system with the sonic choke on it. All right, this is a system, your typical system. This regulator controls it at atmospheric pressure, but there are some places on Earth that have large rapid barometric fluctuations, especially in Canada and the north and in the western section. The fronts come through and the barometer drops like crazy. Well, if you got all your analyzers on these guys, you can see 3% error easily. That's just 1 inch of mercury variation out of the barometer. So we have plants up there that said, man, I can't stand that anymore. These fronts come through and it just throws my analyzers all over the place. So what can you do? So what we can do is we can take this regulator off, and we still use the T right here. We're going to control this header with a absolute pressure controller, electronic absolute pressure controller. So not always in a medieval pneumatic system. So what you do is you take one of these guys right here, which is a commercially available pneumatic controller, electronic controller. That particular brand is a Alley Cat. I don't know if you're familiar with Alley Cats or not, but it monitors the pressure right here and controls it at an absolute value. So it's going to control, typically what you want to do is control this thing slightly above what's typical barometer reading, essentially. Is, say, 30 inches of mercury. Well, your barometers don't usually go too much over that, so you're typically going to stay positive in your header. But it's going, relative to the atmosphere, it can be more or less positive. So you stick a pressure gauge on this thing, that's looking at atmosphere, it's going to be moving around. The guy said, man, the thing's just not controlling. It's moving around all the time. It's moving around all the time because the barometer is moving around all the time, okay? This guy is really nailing it on an absolute value. So another point here is if you really want to control a pressure very accurately, this remote sense right here is invaluable. This is a standard unit with a remote sense. So this unit right here can be on the other end of this building over here. As long as you got this remote sense static line right here, you can control the pressure on this side of it. You don't have to worry about line drop and those kind of things. So it controls the pressure where you want it controlled. That's with that little remote sense right there. And that would fit anything, any application, not just this guy here. All right, so this is a system, it just keeps evolving to handle different scenarios, basically. This particular one, talking about pulsing headers. Well, we found an application on the electronic one where we had the electronic controller controlling the vent header directly. Well, they had the, I don't know if you know what a ARV is, atmospheric reference pressure, it's basically a pulsed pressure coming from the sample loop in an analyzer. Well, it's got to go somewhere. Then they typically dump it into this atmospheric control header. Well, when you do that, these things operate, 15, 20 pounds of pressure with this volume in the sample loop. Bam, you blast that header with that extra flow, and it has to recover. So you can see quarter-pound variation for a few seconds and then back down. So, but that's okay if you got one analyzer, but if you got a bunch of analyzers pulsing into this header, you can cause problems. So what we do is isolate these pulsing flows. You say, well, I got stream switching, double block and bleed. Well, that's no problem. We'll connect that right into the suction of this eductor. So that's not going to pulse the header. It will just handle it up there. And then we have these little back pressure regulators. These are very sensitive back pressure regulators. Actually, they were designed for environmental monitoring where they can control 1 cc a minute type thing for filling up spheres for environmental monitoring at a fence line. You want to fill up an evacuated sphere. That's what you stick on it. And it controls the flow rate into the sphere at a constant flow rate, even though the vacuum in the sphere is changing. So we use these guys here, and what it does is takes the sample loop going into the inlet of it, and outlet goes to this suction over here. So, and then we take a feed that feeds these 3 units with a restrictor. So we typically run the flow going into this guy about 200 cc's a minute. And the flow going from the sample loop goes in there. That's probably a couple of hundred cc's a minute. And it's at a certain pressure. So when you turn this flow off upstream of your sample loop equilibrates to the pressure right here that was already there. And it will not even bobble the pressure at all. So it's a very constant pressure. So you can handle pulsing ARVs and pulsing stream switch valves, and you have a atmospheric, this application wanted a barometric pressure compensation or control. So this is the absolute pressure header that's setting the set point on all 3 of these devices. So it's following barometric pressure, it's controlling absolute pressure and handling all the flow pulses and everything. This is an extreme case. Most people are not going to do all that, but some do. Okay, here's a system with, let's say I don't have any nitrogen, I don't have any natural gas. How do I run this thing? Well, you got to have a pump. So what we do is we take basically what comes out of this system in the suction of the pump and we go to return. We also take a feed off of it, goes back in the unit to operate the unit. So in other words, this feed feeds this regulator right here. So it basically operates without external motive force gases. So that can have different headers on it as well. It's like fast loops can go in right here. It's always a good idea to separate your fast loops. Everybody know what a fast loop is. So it's just an expediting type thing. So you want to get a sample from point A to point B. You take a lot of flow so you get there quick, and then you take a little slipstream off of that fast flow, the fast loop versus your analyzer flow. Okay, that's what one of these guys look like. And it's just the box, yellow box, yellow, orange, whatever. And this particular rotometer is armored rotometer. So a lot of folks don't want glass. We have an armored rotometer. So another picture. There's 2 of them right here. One of these things will handle one analyzer house, and that's some of those houses are longest from here to that wall over there. You'll have 10, 12 analyzers in these things. It'll cost like $3 million or something. So this is one right here, one there, just all over the place. Okay. Surely you guys don't know everything. Got to have some question.
So the needle valve adjustment, that's a manual adjustment?
Yes, it is. That needle valve causes more problems. So when we build things, say, well, we put all these adjustments. So most analyzer guys, instrument guys, they like something to turn, gauges to look at. This could literally be a blind system. No gauges, no rotometer, and it'll function just as well. So if they got a rotometer on there, they're going to turn it. And what happens is when they start turning it, they turn it counterclockwise. And what you're doing is you're lowering how much flow is coming out of the header to the point where the regulator is no longer making up the pressure in the header. So you get an increase in header pressure. So the only way to make this thing work is open it up and let her eat, so to speak. Then you got to take out more than your analyzers put in. So that's there's another adjustment on the side. It's is that vacuum -6 inches of mercury is adjustable. Shouldn't be, but it is. And so naturally, if there's a place to put an Allen wrench, they're going to do it. It's a very sensitive adjustment. So they want to crank this thing around, and it's a very sensitive diaphragm, and they're going to bust the diaphragm. So those are the only real issues with it, is not enough flow going through it, or sticking around with the vacuum controller on it. But these things, they'll run literally for years without any maintenance on them, because there's just regulators in there, no moving parts, usually clean gas, inductors, solid state device, it's relatively clean. They just sit there and run.
So does Parker have a library of different applications you just
Well, I do, but they probably, I'm sure they do. They probably don't publicize a lot of these things. But there's a lot of different applications out there. We haven't found an application yet that we can't do. You got to be a little creative sometimes. So, well, appreciate you guys coming. Yeah.
So Frank, basically, you've got how many base product designs? You showed a lot of different applications. How many basic units do you offer?
Well, your basic unit is just a plain Jane eductor unit. Hundreds of the most, probably 80-90% are going to be like that. And then the other 9% is going to be with mechanical pumps. And the rest of them are kind of like some of these, full window dressing type things. But very few of them. But if you need it, you need it. We can meet whatever the needs there are.
Yeah, different between the gas and liquid sampling.
Well, we don't do liquids. You're talking about in this system, the sampling, different gas and liquids. Yeah, well, you typically treat it differently if you got a liquid sample versus a gas sample. You don't want to put a liquid sample in here. It's a gas sample, and also you need to concern yourself. Well, it's the dew point is such that as it cools, it's going to form a lot of condensate in my system. You need a sloping header and a catch basin to try to keep the liquid slugs, if you will, from getting into this thing.
So the terminology is pump. So when you see pump, you assume it's liquid.
Well, in this case, it's a gas pumps. Yeah. Now the liquid pump, there is a liquid pump in one of these slides to pump out the little reservoir of liquid that you trap out of it. But typically, it's a gas pump, a little ADI gas pump.
The inductor would not work with liquid anyway.
Well, they do, but you don't want to put liquids in your system, basically. Yeah, you don't want to put air in it either. So it goes to the, you only get to do that once. So. Exactly. Yeah. So. Okay.
Yep. And anyone online wants to ask a question, feel free to chat in, or I can unmute your line even if you want to ask it live.
Frank, thank you very much.
Sure.
If there's no other questions, we will see you at the next meeting, which will be the Fab Lab. So check the website out for information on that. Date again, Wayne, was 13th of August. Same time, but at Delgado next time, obviously in the lab. And yes. and we'll get more information on that. It's posted on the website. You can already register for it today as well. But I look forward to seeing you all out there, and we'll hang around for a little bit. If any other questions, any other housekeeping news there? Okay, all right, thanks.